Hey everyone, welcome back to this week where we're going to be learning about linear regression and correlation. And this week and next week, our lectures will go together. So this is kind of like a step one into this topic. Next week, we'll be looking at a step two, where we really will focus more on hypothesis testing. This week, we're going to learn what do we mean by linear regression? What do we mean by correlation? And how do we find the line of best fit, which is really a question that simple linear regression answers. And then we'll also talk about correlation and how that basically is closely tied to the regression line and the regression slope. So this week we'll be talking about linear equations, and it's really our first dive into modeling. It's important to note that at this point we're still talking about bivariate procedures. That is, we're comparing two variables. We can call them X and Y, or we can really call them anything we want. And what we're going to be doing is looking at two-dimensional scatter plots this week. We have an x-axis, a y-axis, and we'll be talking about linear equations, lines, which I'll introduce in a second. Now, before I get on to that topic, I want to just say briefly, what we're assuming here this week is that we want to compare two numeric variables. And the basic question we want to ask is, are they associated? That is, are they correlated or are they not? If they're not correlated or associated, that means that we have evidence that the two variables are independent. And so an example, weight and blood pressure in a sample of adult males, these are both numeric variables. You might suspect they have some degree of correlation, and it's the researcher's interest to uncover that correlation. So let's get introduced to linear equations. And the reason why we're starting with linear equations is because both simple linear regression models and correlation, they both are measuring the degree of linear association between two variables. So we need to really dive into what we mean by linear association. And really what we mean is that there's some equation, a linear equation, that we can use to summarize the relationship between X and Y. And if you think back to, the SAT math you had to study for even before that in high school and maybe middle school, or we learned about these two-dimensional plots, we call these Cartesian coordinate planes, these things that have, they span in the X dimension or direction and in the Y dimension and direction. And that's why they're 2D, right? We contrast that with 3D, where you can move left, right, but also up or down. We usually call that third dimension a Z dimension. So this week, we're looking at only two-dimensional planes. And if you remember back to how we define or describe any line, we use this equation, at least this is what we use in the US, y equals mx plus b. And I hope that looks familiar. We have two parts of that make up a line. The first thing we have is the slope, which is the m, and then we have the y-intercept, which is the b. And the y and x, these are just the variables, the input and output. If you know the slope and the intercept, if you give me some x, the line will give you a number for y. And if it's a perfect linear equation, it gives you the perfect prediction of y. But we're in statistics. These lines are summary vehicles. They're never perfect. And so we actually, when we get to a simple linear regression model, we'll add a little epsilon error. But for now, let's just talk about the nuts and bolts of a linear equation. So I gave this problem I kind of made up. This is kind of like one of those classic problems for SAT math. It's a lemonade stand problem. So this problem I've set up, we have a little student, Sally, who's in the fourth grade, and her parents decide, hey, let's incentivize Sally to set up a lemonade stand. We think she'll learn some valuable things from operating her little lemonade stand for the day. So to incentivize her, her parents decide, we're going to give you $10 of cash just for opening the stand. Okay, so that means, let's say that Y is the revenue that Sally generates from her lemonade stand. We'll let X be the number of cups sold. That means if she sells 0 cups, the X coordinate comes first, right? she will still bank $10 because her parents gave her that startup investment, right? So even selling no cup, she still earns $10, but she can also earn revenue from selling cups of lemonade. And she decides she's going to sell each cup of lemonade for 50 cents. And so what I've just given you here is basically the slope and the y-intercept. So let's start with the y-intercept. The y-intercept is the value of y when x is 0. That is, it's the point where the line intercepts or touches or intersects the y-axis. So in our example, the y-intercept is 10. And that's because, again, if the intercept is the value of y when x is 0, well, if you plug in 0 for x here, 0 times 0.5 drops out. You're left with only 10. And graphically, this is what it looks like. The line passes the y-axis at exactly that point, 0, 10. So that's the y-intercept. We also have the slope, and the slope is basically the part of a linear equation that communicates how strongly x and y are associated or how much x and y change together. So in this case, every time she sells one additional cup of lemonade, she earns 50 cents. And so what this means is that 50 cents is the slope of our line. You might remember our teachers used to call this rise over run. It's also synonymous with change in y over change in x. Let me write that down here. Change in y, that's the Greek letter delta. It's like a little triangle over change in x. So again, every one additional cup of lemonade she sells, she gets 50 cents, right? So that is our slope in this line. And the thing that linear equations can do is, given an equation, I'm using here Desmos graphing calculator. It's actually a pretty good tool. I'll reference it a couple of times today. But you can see I put in my two-dimensional line. I have a y and x variable. Those can take any value depending on a particular problem, right? I mean, y can't be negative, I suppose, because there's no scenario in our little problem where she could realize negative revenue. And then X, she could sell any number of cups. Again, technically shouldn't be negative, but I haven't imposed those constraints on this little thing. I've just drawn out the line, and you'd have to be logical. You know that she has to sell 0 or some positive number. So really, this is the part of the line that's relevant for our problem. But as you know, the equation of a line goes on forever. So even though there's parts of this line that are not useful to us, it still goes on forever. And if you look at this line, you can see here that when I sell 10 cups of lemonade, I should get about $15. And you can see exactly there, 10 cups of lemonade, that's the X, gives me $15. And you can, by the way, with Desmos, come and put points on your 2D system. So basically, the line gives you the set of all X's and Y's that go together. So you can take any number of cups she sells, plug it in this equation, gives you basically a forecast of her revenue. So all that to say, there are two parts of a line that we really care about. There are two parts of the line that we need to understand if we're going to be successful in mastering this week's material. That's our equation. And what we're really interested in is B, the y-intercept, and M, the slope. Now, this right here is a linear equation. All the points will lie on our line. We know in the real world that usually problems are a little bit more messy. So if you make a regression of, say, height and weight, generally the taller you are, the more you weigh. But we know it's not a perfect relationship. And so all the points will not lie on the line. And once we're in a situation like that, that is, we're really modeling like social phenomena, we're going to have to use a slightly adaptive version of this linear equation. We're going to use something called a simple linear regression equation, a simple linear regression model. And it's the same thing, it's the same equation, We just add error to it, and we'll be talking about that error here in a second. And so when we go to simple linear regression, we often write the notation a little bit differently. And you can write this notation actually however you want. Give me 1 second because I think, yeah, I need to update this. Give me 1 second. Sorry, guys, it's just going to take 1 second. I forgot to update my PDF version. Why is it this? Oh, okay. Great. Okay, here we are. So one thing I do need to do is make sure I close this one. Okay, so when we look at the line, the regression equation for a simple linear regression model, instead of writing y equals mx plus b, there's two really, really common ways that you're going to see people write a regression model. So we can have beta 0 or alpha or a, always lowercase. These could be the y-intercepts. And then beta 1 or little b, those are going to be the slopes. So b or beta 1, that's m. And then beta 0 or a, that's going to be the b part of here in our old formulation, y equals mx plus b. Now, one other difference you're going to notice in how we write simple linear regression models is that we put the intercept first. So you can see I wrote beta 0 and a, which are intercepts. Again, you can write it however you want. These notes will use both ways. And I know it's confusing, but I wanted to write it both ways because it's important to realize that it doesn't matter how we write it. And it's such a common topic of study. And it's basically the very next thing that you, if you're interested in quantitative methodology, the next step will be continuing to learn these regression methodologies. You're going to see people writing these parameters in all different ways or estimates of the parameters. So I just wanted to, I'm going to interchange throughout the notes today, but it's important to note that it doesn't matter what we write. What matters is that you can recognize that beta 0 and a or alpha here, these are intercepts. And we know that because there's not another variable like x attached to it. And the reason why we put the intercepts first is because when we get to multiple regression models, you can keep writing out terms here. So I could write plus b2 x2 plus, so I can keep adding variables to that. Now, we're not going to touch on multiple regression this week. Maybe next week, we'll see. I haven't fully made up my mind on what that lesson will look like. But that's why we write the intercept first, because it allows us to continuously add new variables and slope estimates for those new variables. But this week, we're in a bivariate case. That is, there's only one x, one y, and no need to write other variables now. Okay, so let's get a little bit more into simple linear regression. So I have a little example here. We have height and weight on the weights on the y-axis, heights on the x-axis, and you can see we've just put a bunch of dots. So you can imagine we've collected a random sample of observations of people. We measure their height and their weight, and we make this plot. And we fit what we can call the line of best fit, or the simple linear regression line, also called the OLS, or ordinary least squares regression line. All these are names which indicate the same thing. And what this line is really doing is it's describing the relationship between height and weight. In particular, you can see there's a positive association. That means on average, as weight goes up, height generally goes up too. That's not always true. You can see here we have someone who is height of 45. I guess that's inches. And then we go to 50 or 55, and you can actually see the weight actually maybe even goes down for those three individuals. So these regression lines are describing the average trend. And there's really two reasons why we use these regression lines. The first is exactly what I just did. I used it to describe the relationship between X and Y. That is, it's an associational thing. The second reason why we use simple linear regression lines is trying to understand which model or covariate or X best predicts the outcome variable Y. And so this is like a predictive thing because if you take someone's height and you can go to the regression line, you can get a prediction for their weight. And so describing or predicting are the two main reasons why you're going to use regression models. And you can also use regression models for causal inference, but that is a more advanced topic, which we won't have time to cover today. I'll just say now that, as the old saying goes, correlation is not causation. So causation requires a deeper set of stronger assumptions about how X and Y are related. Okay, so we're introducing and thinking about a new bivariate procedure for two numeric variables. And so, as we've done all semester, the first thing we have to talk about is this idea of population parameters. And again, I've drawn this picture many times through the semester, but if I have a population parameter here, alpha, what I want to do is get a sample of data, maybe I call it little a, and I use that sample of data to estimate it. So in our simple linear regression world, you can see here the first equation, we have an alpha, which is our y-intercept, and I want to estimate that. And so the alpha, the thing we write in Greek, is really the parameter, and then beta is our slope. And I wrote little a and little b because these are one way that you can write that a is an estimate of alpha and b is an estimate of beta. And what that means, again, they're estimates. Why are they estimates? Because I take a random sample. I can't sample all 7 billion people in the world. If I want to know the exact association between height and weight, not possible. So I'll take a random sample of maybe 100, 1,000, depends on what I'm trying to do. I'll estimate little a and little b. Sorry, I'll estimate alpha and beta rather. My sample gives me A and B. And note, you can also write, as usual, little hats. Sorry, that was a little off there. So I can write beta hat, and those can be my sample statistics, which are estimates of the population parameters. So the hats also indicate estimates. And so, okay, we looked at the first two parts of our line, the intercept and the slope part. But you'll notice that there's a third population parameter here, and that's epsilon. And so really when we're going to be talking a lot about epsilon, that's the error in the model. And we can call that the residual or the error. And again, we're going to be talking about and focusing on this a lot because these regression models, they give us linear equations, but the linear equations are not perfect, right? And we saw this idea up here. Let's go up here. So, given this regression line, you can take a prediction for a given weight, but you can see there's always going to be some error, right? It's not perfectly reproducing everybody's height and weight because there's not a perfect deterministic relationship between height and weight, right? It's statistical or probabilistic. And so that error is what we're going to spend a lot of time talking about today. And so there's two parts of a regression line, right? There's what we call the fixed part, and that's the actual line. It's got the intercept and the slope, and it's fixed because once you have your sample of data, it's just never going to change. And so if you want to use it for predictions, so take the height and weight problem, I just need to measure someone's weight and then the expected value of y, that is the average y value. It's the mean y value. Well, that can be predicted by just plugging in that person's weight once I have an estimate of alpha and beta. And so we call that the fixed part of the line because it's fixed. It's just a line. You know, once you know the line, it goes on forever, right? And when we interpret these parameters, we have the intercept and slope parameter. And so, you know, alpha is the average value of y when x is 0. So in a line, it's the value of y when x is 0. But in a regression problem, it's the average value of y, the average y when x is 0. And that's again because it's not perfectly deterministic. So you can imagine that if I have this down here, the error has a normal distribution. So for the y-intercept, you know, there's going to be some error there. And this normal distribution, we kind of draw it around the regression line. You know, that's going to govern how the size of your average error. And we'll be talking more about it, but it's in a regression context, it's the average y, right? We're describing average trends. And beta, it's our beta 1, it's our slope parameter, and it really gives the relationship between x and y. And so how you interpret this is for every 1 unit increase in x, we expect y to change by beta units on average. You can also say that as beta is the effect of a 1 unit change in x on y. So the intercept and slope, they have the same interpretation as a linear equation, except the word on average should be added there. And we also have the random part of the model. That's the epsilon here, Greek letter for epsilon. And the residual is the difference in someone's score, that is yi, and what the regression line predicts. So we can say yi, this is someone's actual. So again, I is an index. So y1, for example, is the actual weight of person 1. Y2 is the actual weight of person 2, etc. That keeps going forever. But the regression line, if I put a little hat here, can give me a prediction for person 1. It can give me a prediction for person 2. And the useful thing about this, if we can generate predictions, is it's the difference in these two things. yi minus y1, y2 minus y hat 2. That gives me the prediction error for each individual. And all we're doing here, like the expected value of yi, well, we know that y hat 1 equals alpha plus beta 1 plus whatever their x is. So you have to multiply x by beta, and then you add it to alpha, and that's how you get the prediction. So we're just plugging in for expected value of y, the regression line that we're estimating. And you can also see this up here. The expected value of y, again, it's the fixed part of the regression line. So all we're doing is subbing in there the fixed part of the regression line. And again, what we're doing in this third step is emphasizing that you can use whatever notation that makes sense to you, or that you prefer, different books, different stuff you look at online for online help. They're all going to be using different notations. So we really got to get used to this idea. You know, when we studied the mean parameter, right, we talked about this where we take a sample, compute x bar, we use it to estimate mu. Everyone writes mu in the same way. So, you know, here that's not going to be the case. Everyone writes, if we take the sample variance and we use it to estimate, pretty much everyone uses sigma squared, the Greek sigma with a square on there to represent the variance parameter. So here there's a little bit of ambiguity because we all do use different things, but you'll be able to tell by how they're written, you know, this is clearly the intercept, this is clearly the slope, because the slope has an x attached to it. So as x goes up by 1, y changes by beta units. That's the idea here. And so because the regression line doesn't perfectly recreate the observations, you can see these green dots, that's the yi's. The y hat i's fall on the regression line. There's error. And so the question is, you know, really, if you think about a line of best fit, how can we create a line that minimizes these errors, right? So there must be some strategy that gives me the optimal line, or the degree of error, that is the degree of mismatch between yi and y hat I, is at its smallest. And so what we're going to do is we're going to see that there's a way that you can estimate beta 0 and beta 1. That method is called ordinary least squares regression, or the ordinary least squares criterion. That when you use that method, it actually gives you the optimal regression line that will minimize the errors. And so what we're going to learn next is really about, what is that formula and how do we actually find that answer? So let's go ahead and start talking about how do we generate that answer. And we're going to start by thinking about a hypothetical example. Suppose that you had this data, X and Y, where Y is height, Y is weight, X is height. You can imagine you get this data, and the question is, how can you find the optimal line? Because some people might say, the optimal line could go there. Some people might say it looks more like that, right? There's different ways that you could imagine you could use a line to describe that association. And so there's some ideas. You could imagine creating a line where there's an equal number of points above and below the line. But the issue is, even if you have, like, say, 10 points above, 10 points below, the points above there could be much more error in the points above the error as below the error, as below the line. So that's not going to really give us the smallest amount of error, right? Maybe we should just make sure that the average error adds up to 0. So, if I add a line here, this has a positive error because it lies above. This has a positive error because it lies above the regression line. This does not. And remember, the errors are yi. Each point is a yi minus y hat I. So if your data lies above the line, that is yi is greater, you get a positive prediction error. If this is bigger, the prediction, that is the regression line, than a particular observation, then you get a negative. So you could imagine, well, what if the errors just add up to 0? The issue with that is it turns out there's many lines that satisfy that approach. And so you might also think, well, maybe I can find another method that kind of takes into account the magnitude. And this is exactly what OLS actually ends up doing. It actually concerns and focuses on the magnitude. And so, this method was developed by this old mathematician named Gauss around, I think it was, like, I'm going to say 1890, maybe, something like that. He was actually studying heights and weights, was the first regression problem. And so he basically came up with this criterion called ordinary least squares. So if I take yi and I subtract the error, I subtract the prediction, so that's just y hat I, right? If I square that and sum it, that is the sum of the squared residuals, epsilon sub I squared. If I actually minimize this value, then it leads to actually the optimal line of best fit. So you don't need to really learn about how Gauss came up with this. There's a little bit of notes on that below. What we're going to go do now is actually talk about what are the values of alpha and beta that give us the line of best fit. That's really our interest today. What that means is we want to start making estimates or inferences about the parameters alpha and beta, the intercept and slope. So the idea, again, is we would get a sample of data and we would need to estimate these alpha and betas. And the question is, what is the strategy or technique we use to actually estimate them? Is there some equation? Is there some method? So what we're going to do is we're going to learn that basically Gauss discovered that these are the formulas for the optimal alpha and beta. And I don't want to go into it too deeply. I will say if you're going to continue studying quantitative methodology, you should really go slow and take your time learning linear regression because these techniques are really the foundation of all higher level statistics. And the class that's usually taught right after this, applied regression, it's a full semester on this topic. And even as you go beyond that class, like you go to multi-level modeling, you go to multivariate methods of analysis, structural equation modeling, you'll always spend like a couple of weeks reviewing simple linear regression and multiple regression. Multiple regression, I think we will touch on next week. And so, Gauss uses calculus to show that these are the equations that give us the line of best fit. So if you look at alpha, what we're going to need to do is I'm going to give you two columns of data, an X and a Y, and you're going to have to basically come up with alpha and beta. And so the alpha is pretty easy, right? You just take Y bar, that's the average Y, X bar, the average X. You should be very good at that by now. And then you just do Y bar minus B times X bar. Okay, well, you might say, what is B? B has a little bit more complicated of a formula. And so B is equal to the sum of the product of the X and Y deviations. So remember, a deviation is you take a column of data and you just subtract the mean. And when you do that, again, we call that centering. So we're taking the X and Y deviation. You'll recognize this because in your z-scores, how do you z-score a variable? Well, you do yi, let me write this out. So the z-score is yi minus y bar, right? You take each person, subtract the mean, and then you also divide by the standard deviation of y. Now, all we're doing here in this numerator is we're just taking the deviance. So you can kind of, hopefully that yi minus y bar is familiar, and you also have xi minus x bar. So that's the top. We're going to multiply the deviations for each person, and then we add them up across all the people in our sample. And then in the in the denominator, we divide by the sum of the squared deviations of x. So this is actually an equation. We don't need to understand the proof or anything about how Gauss got there. All we need to understand is how to use these equations, and we need to understand, they're the building blocks of a linear equation. That word linear is extremely important this week. Okay. So I'm going to come back to a computational example, a math problem, at the end of these notes. So for now, I just want to keep focusing on the logic of simple linear regression. So if we're going to use the OLS method for estimating alpha and beta, why is this give us the optimal solution? We've already said that there were multiple lines that you could draw that, for example, give you zero error. Well, it turns out that Gauss and Markov developed one of the most famous theorems in statistics called the Gauss-Markov theorem. And what it basically says is that the OLS estimates, that which we saw above, the OLS, I should say, estimators of alpha and beta, these are blue. That is the best linear unbiased estimators. So I'm not going to go too much into what this means, but unbiased basically means that if you were to conduct an infinite amount of trials and you were to take the average alpha and beta from those trials, your estimates of alpha and beta, they would actually equal a true population parameter. So we've seen other examples of unbiased estimators this semester. So remember, X bar has a distribution. which is normal. It's got the true parameter mu at the center of the distribution, and then it's equal to, what is this? This is um, the standard error of the X bar distribution, or its variance, is actually going to be, I think this is actually the standard deviation I wrote, but right, it's sigma over n over the square root of n, and that's going to be the standard deviation. So I wrote the standard deviation rather than the variance there. But the important point is that at the middle of the X bar distribution is mu. And this is actually what we mean by unbiased, that if I were to take an infinite amount of X bars, and everyone can get X bars all over the place, right? But if you average them together, you actually get the thing that you're trying to estimate. And so if the distribution looked like this, the average would not be mu, right? If my X bar distribution was blue, but the parameter was that mu I drew at the bottom there, on average, I'm getting a biased estimate. So this property of unbiasedness is really important. It's a advanced topic, I would say. And all you're expected to learn in this class and the next class is that the reason why we use these OLS regression methods is because they are blue, best linear unbiased estimators. And what the best word means there is there's the smallest amount of variance. The standard errors are smaller than any other possible. And so that is, again, it's a very advanced concept. The only thing I expect you to know is, hey, there's this thing called the Gauss-Markov theorem that says this line of best fit based on this alpha and beta estimate, that's the best line we want. And there's complete agreement in the scientific literature that this is the optimal way to describe a linear relationship between X and Y. Okay. So at the beginning of the notes, we talked about two goals of simple linear regression: description and prediction. And so far, I've really mostly focused on descriptive. I've talked about X and Y, about how, beta is really a summary of how X is related to Y, because beta means for a 1 unit change in X, Y goes up by beta units. So we also really care about prediction. And again, it really depends on your research question. I would say most researchers have a more descriptive question, but when you leave science and you go into the private sector, they really do become more interested in predictive rather than descriptive questions. And there are some fields where prediction might be more important than description. So what we're going to talk about now is measures of model fit. That is, how do we know how good our line is actually predicting the data? And so again, we're going to continue with our weight example. So we're going to put weight on the y-axis. And you can imagine I can make a simple linear regression model using height or age. And so there's two little fictional pictures here. And the question is, which is better for predicting weight? And it looks like I actually cut off a little bit here. I'll fix that in the notes before I post them. And so how do we actually measure model fit? Well, we use this really famous statistic you may have heard of called R squared. And so for R squared, what I want to do, I'm going to use this. I'm going to derive it, my own diagram. So 1 second to switch my share screen. Okay. Okay, so this is, I'm going to just use this and refer to this. I thought I could copy and paste this, but I guess I can't here. Okay. So what we're going to do is we're going to go through an exercise here. I have my x-axis, I have my y-axis. So let's say I have a sample of data, right? Draw that positive relationship here. And I have a regression line. What I want to do is I want to focus on one particular point here to motivate this example. And this particular point, we're going to call this person Y1. So if I were to try to predict Y with one number to give me the best prediction, what would that number be? What's the one? Let's say I didn't know anything about X. I want to give, all I have is my Y data. I have a column of heights or weights if I want to predict weights. What would I do to give me the best prediction if I didn't know anything about other variables like, what culture they're from, how old they are, what their heights are like? What's the one number that would best predict weights? Well, that number would be Y bar. It would be the average weight, right? If you couldn't use any other information, then you would just use the average Y to describe and ground your prediction. So when we actually compare model fit statistics, we basically use Y bar, the mean of Y, as a very important reference point in telling us how well the model fits. Because if the model can't better predict height than Y bar, the model's completely worthless, right? You might as well throw it away, just take the average weight, and that's my best guess because X won't tell me any more information. So here's what we're going to do is we're going to always use Y bar as a reference point. So this right here is my regression line, and I can write Y hat. That indicates the regression line. Now, if I were to, so this person, right, they have, I'm going to switch my colors out here. So they have this value of X. We'll call that X1. So this point right here, that point, we call it Y hat 1. That's the predicted value for that person. And we get that prediction value because we estimate the regression line and we just plug in their value of X1. And then we have the intercept, which is over here. And then we have the slope. We need both of those things. So again, how you get the Y hat 1, it equals the slope estimate, sorry, the intercept. I'm going to write with alpha plus beta times X1. I'm literally just plugging in the X1 and I'm using the least squares estimates for alpha and beta. So it's just like I've got this regression line now, and what we're trying to do is quantify how much error there is in the model. So if I take this person, their yi is up here, right? This is the actual observed data point. It lies far away from our prediction. Our prediction for them is down here based on their x, right? Because the prediction, remember, it's the average prediction, the average trend line. And so if my worst case scenario is using the mean, Y bar, I can basically think of all of this as the total variation between Y bar and each observation, right? And that's like the total variation, that distance between the average in each person. That tells me how much deviation there is from the mean. And what we do is we write this as the total sums of squares. It equals yi minus y bar. And it's the part on the left side of this equation here. And so, and I think, I don't think you can actually see this. So let me let me keep going. So this is the total sums of squares. And then again, that's just for one person. You know, I'm focused on one particular person here. But if I were to take the all the variation for everyone and sum them up and square them, then I get basically the total variance in the data. And if you actually remember the formula for variance, it's actually the sum of yi minus y bar squared over n minus 1. This is the estimate for the variance, which we have covered in the class before. You'll notice that the total sums of squares, this numerator is exactly what the total sums of squares is. So the total sums of squares, it's really the same thing as variance, which we've already learned. It measures the amount of dispersion or spread in the data, but the variance divides by n minus 1. The variance is kind of like the average dispersion, if you will. The total sums of squares, we're just looking for the total variation in all the data. We're not trying to average it out. So this basically tells us how far each person lies from the mean. That is how much variation is there, which the mean does not tell us about. Now, the next thing we can do is we can start partitioning out the explained variance. So this chunk right here. So if I have the total variance as the red, this little green, that brought us from y hat to the regression line. This is actually what I like to call the explained variance or the regression sum of squares. And so the regression sum of squares, if we were to write it, reg sums of squares, this is, again, the difference from y hat I minus y bar. And again, for each person, we're going to square it and sum it. So you notice, again, we're squaring these terms. Why are we squaring it? Because we're trying to get rid of the direction of deviation. Because, you know, if I lie, let's take like, so this point right here, if I'm looking for this person, y hat I is bigger than y bar. You can see there's a positive number there, right? But look, for this person down here, if we're down here, all of a sudden that is going to be negative because y bar is greater than y hat I. And so when we measure the total explained variance, we don't care if it's a positive or negative direction. What we care is the amount of explained variance. And so by squaring it, you know, if it's 2 or negative 2, we don't care. We're scoring a 4, right? Because negative 2 squared is 4, 2 squared is also 4. So when we square this stuff, it's exactly the same thing, and why we did it for the variance. We're ignoring the direction of deviation from the middle, from y bar, and we're only going to be measuring the magnitude of deviation. And then finally, we sum them to get an overall example, an overall estimate of the explained sum of squares or the regression sums of squares. And then finally, we have the residual sums of squares, or the error sums of squares, which we can call RSS. And this is actually going to be here. So for this particular person, although the regression line got us a little closer to their observation here, there's still a whole bunch of variance that is unexplained because their true observation is still way above the regression estimate. And so that right there is still the error in the model. And so if I write that out, that's going to be yi minus y hat I. Again, I squared to get rid of the direction of deviation, and I sum it to get a measure for the overall sample. So the regression sums of squares, I like to think of this as the explained sums of squares. And I like to think of the residual as the unexplained variance. So they have different names, different textbooks are going to use different acronyms. You know, the acronyms I'm using in the notes are basically what I'm going to be using throughout the class and in the last few weeks here. So just get comfortable with the notation in the notes, and the book will maybe use slightly different notations here. Every book will, but I would just try to be consistent with what I'm putting in the notes here going forward. So if you're going to study a notation, I would just learn what's in the notes for now. And so basically what we're doing then, we have three parts here. We have the total variance, the explained sum of squares, and the unexplained sum of squares. And it turns out that you can just write this as total sums of squares equals the regression sums of squares plus the residual sums of squares. And so what we're doing is we're basically taking the total variance and we're partitioning it or breaking it up into two chunks. The variance which we can explain and the variance which we cannot explain. And it turns out that R squared, our measure of model fit, is basically regression sums of squares over total sums of squares. So really, R squared is the proportion of variance and Y which the model is able to explain. And wait 1 second. This also equals 1 minus the error sums of squares over the total sums of squares. So again, R squared is a very, very famous statistic, which you may have heard of coming into this class. And it's basically a number that goes from 0 to 1, because you can see here, it's a percentage, it's a proportion. It's the proportion of explained variance to the total variance. And it goes from 0 to 1 or 0 to 100%. Numbers closer to 100 are better. That means you're able to describe more of the variation in Y. And so these equations, which I just derived geometrically, there's also a lot of good visualizations in the book, online. This is a really extremely important concept. So I think it's good to focus on really understanding what these three things mean. And of course, this is basically a picture of what I was just drawing here. You know, we need to understand R squared and how to calculate it. Okay. So I'm not going to spend much time talking about this next part, but there's really two ways to measure model fit in a regression context. The first is R squared. That's the most common, the most useful that you will see because it's standardized. So, you know, you can compare R squared from one model to another model, even if it's different variables. But we have this unstandardized measure, which turns out to be more useful the more you study statistics, called the standard error of the regression line. And we can also call it the residual standard error. And it's basically the amount of variation in Y not explained by the model. So, you know, I'm not going to test you over this. I will just say that as R squared goes up, the standard error regression line must go down, right? Because in this case, you have more explained variance, so you have less unexplained variance, right? So the two are inversely related, but I'm going to be focusing mostly on R squared as a measure of model fit. Okay. So to review, what we just went through is the building blocks of simple linear regression. Remember, simple linear regression, there's only one X and one Y, which means it's a bivariate procedure. And importantly, it only considers the linear association between X and Y. Now, we have a standard measure called the correlation coefficient, or Pearson's product moment correlation, that you can also use to describe the linear association between X and Y. And we usually denote this statistic with a little r. And note that R has a very, very close relationship with our regression slope B. And there's actually an equation here. You can actually convert back and forth from B to R if you have, so B equals R, the correlation, times the standard deviation of Y divided by the standard deviation of X. You can invert that and say that R equals the regression slope B times the standard deviation X divided by the standard deviation of Y. So correlation then is really, really closely tied to simple linear regression. And again, correlation, you are going to have, by assumption, two numeric variables here. I will say this can actually work on categorical data if it's binary. So if you have a 0 or 1 variable, you can actually correlate that with a numeric variable or another 0 or 1 variable. And when you correlate two categorical variables, we actually call it a phi correlation or phi coefficient, but it's actually the same exact thing as this. So generally, when I talk about the correlation this week, I'll be referring to two numeric variables. But no, this also works for binary categorical variables. Now, before I get into interpretation on the correlation, I want to note that we just talked about R squared as a model fit measure, right? I'm talking about this R squared. It turns out that if you square root that R squared, you actually get the correlation R. So there's actually two ways that the correlation is related to a regression context. So we started out here by learning how correlation is related to the regression slope in a simple linear regression model. I want to now broaden our viewpoint and focus this a little bit more on like how do you actually interpret a correlation, what does it actually mean, etc. And then we're going to finish and conclude today by looking at some computational examples. Okay. So there are a few things that a correlation statistic communicates. The first thing that I'm going to say again is it is bivariate. That means it's telling you how X and Y are related. So since the midterm, we've learned about a chi-square procedure. That's a bivariate procedure that requires two categorical variables. We also learned the t-test, which is a statistical procedure that's bivariate. That, in that case, there's one numeric variable that should ideally be normally distributed. So one normally distributed numeric variable and a binary categorical variable. So we learned how to relate a categorical to a numeric with the t-test. The chi-square taught us how to relate to categorical variables. And now we learn correlation or simple linear regression, which are equivalent procedures that tell us how two numeric variables are related. So again, a lot of the emphasis since the midterm has been on different bivariate statistical tests. And this is the last one that we're going to learn that compares two numeric variables. So the things that a correlation statistic will communicate, the first is the direction of association. So this is basically can be positive or negative. If it's positive association, that means that as X goes up, so does Y. If it's a negative correlation, that means there's a negative association, and as X goes up, Y goes down. So for example, a positive correlation, depression and anxiety. On average, as depression goes up, anxiety goes up as well. A negative correlation, temperature and household consumption. As the temperature drops, the household needs to consume more energy to keep it heated and warm. Right? So there's an inverse relationship or a negative relationship between X and Y in that example. So the first thing that a correlation statistic will tell you is the direction of association. And there we actually just look at the sign. So you see that's a -1, -0.9, -0.4. Notice how as X goes up, Y goes down. Or as Y goes up, X goes down. Positive correlations, they go up together. So that's the first thing that we need to be comfortable interpreting in a correlation. The second thing is the magnitude or strength of association. So, if you have a 1 or -1, it's a perfect deterministic relationship, and it's actually just a line. That lemonade example that we started today's class with, that is actually an example of a perfectly deterministic relationship. And you can also see 0.9 and -0.9. Notice it's very strongly linear, but the points are not exactly on the line, but the line does a really good job at really describing the relationship there. And as our correlation weakens to 0.4 or -0.4, you can see the line still does a decent job, but not as good, clearly, as the 0.9 or -0.9. And finally, when you get to a correlation of 0, there's no linear association between X and Y. If you were to actually draw a line of best fit through that data, you would actually just get a 0 regression slope like that. And so a correlation of 0 means the slope between the lines is 0. That is the B or beta, the slope parameter in a simple linear regression model is 0. So the two things that a correlation statistic communicates is direction and magnitude of association. And we can use Cohen's 1988 guidelines to understand what a small, medium, and large correlation is. So a small correlation, if it has a correlation of 0.1, that's small but meaningful. Medium is about 0.3, and large is 0.5. And I want to know about the strength of a correlation. You can have a 0.5 correlation or a -0.5. These are the same magnitude, right? So that's why we're talking about an absolute value here. It doesn't matter if it's positive or negative. What we care about is the absolute value. That's what tells us how strong a relationship, a linear relationship between X and Y are. So, one way that I really like of describing a correlation is this little thing I've underlined here. I've heard some people call it the degree of scatter around a regression line. And to me, visually, that really makes sense. You can see that the 0.9 versus the 0.4, there's much more scatter around the regression line here, right? So that's also another useful way to think about what correlation means. And again, I've said it over and over. We must remember that the correlation measures only linear relationships. So this last graphic drives that point home. So again, if you're in a 1 or -1, the slope can be anything, but it's a perfect relationship. As a 0.8 or -0.8, -0.4 or 0.4, you can see there's definitely a linear relationship. You can imagine fitting a line through there. And the degree of scatter increases as you get closer to 0. And then finally, by the time you're 0, it's just a perfect cloud. So these points we reviewed above, down here, you can see that X and Y actually have really close relationships. But the correlation statistic is 0. And again, this is because a correlation only measures a linear association. So if you fit a line through these, in every case, you're going to get a flat line like this. And the slope of that line is 0. So even though there's clearly a strong relationship between X and Y, our correlation statistic will not pick that up. And if you have data that looks like this, and you'll see data that looks like this, clearly a curved line is the best model there. But if you estimate a correlation statistic, it's basically just treating it as a flat line. And you probably will get a better measure of the association if you can account for that curvy linear relationship. And there are ways to do that. It's just beyond the scope of our class. So correlation, which you will see continual references to as you study and read more scholarship, it's only measuring linear associations. Cannot emphasize that enough. Okay. So we've learned the theory now, the nuts and bolts of what we mean by simple linear regression models and also correlation statistics. So we need to dive into some practice problems, and these practice problems are representative of the type of practice problems that I expect you to be able to solve on the homework and also the final exam. So these problems, I'm always going to give you an X and Y. I'm going to have to give you two columns of data because we're interested in how these two numeric variables correlate or how they're related. And what we're going to do with this example, we're going to use this example to compute both the correlation and the regression slope. We're going to see how they're identical. So one of the first things you might do when you have two numeric variables and you're interested in studying how they're related is you might just create a little scatter plot, which I've done here in Excel. And I will say that this is going to be included, all the math here is going to be included on Canvas and an Excel file. So let me open up that Excel file just to show you. So I wanted to make sure that I gave you an Excel sheet because Excel is probably how I recommend computing this, but you'll see that I will also make sure I'm sharing my whole screen. You'll see that I also show you how to do this in SPSS. Okay, so here is my X and my Y, and this Excel sheet has practice and practice keys. So what I would suggest you try to do is do this on your own. I'm going to run through it as I have it in the notes, but I've filled out everything you need to do. You can see there's 3 steps: univariate statistics for X, univariate statistics for Y, covariance between X and Y. There's also this other method on z-scores, which um, I have not talked about, but next week I will come back to. So we'll keep the z-score stuff. I mentioned the z-score stuff today, but next week I will really talk about how to use the z-scores to calculate the correlation too. And actually, oh, it looks like I actually put it at the bottom of these notes. So I will actually conclude with that then. So let me get back to my example. So you should be following me here in the notes. And so again, we have an X and Y, and I've created a scatter plot. It definitely seems to me that there's a linear association between the two. When I see a scatter plot like that, the first thing I start doing is just saying it's supposed to be a straight line, just imagining a regression line describing that association. That's how I'm visualizing whether there's a linear association or not. Now, what we're going to do is we're going to actually compute the correlation here. And so the formula for correlation is right here. So R, remember we use that to denote the correlation coefficient, and you don't have to, but here we've put subscripts on X and Y to just indicate it's a correlation between X and Y. And so this correlation formula has got 2 components. It's got a numerator here, which is the covariance of X and Y, and it's got a denominator, which is the standard deviation of X and the standard deviation of Y. What this means is 2 things. A, you should already be comfortable computing the standard deviation of X and Y. So hopefully that is something that you feel confident about already doing. It's the numerator that we need to learn a little bit about. And so the covariance, it has this formula up here. The sum of the deviations divided by n-1. So you can compute the covariance and then the standard deviations and then just plug it into this formula. And we'll see how to do that in a moment to get the correlation statistic. It also turns out that you see the covariance has an n-1 here. When I actually plug it in the formula, you'll notice the n-1 disappears. So, where did that go? Well, if you also remember the standard deviation of X and the standard deviation of Y, those also have an n-1 in the denominator. And so that n-1 is actually in the square root. So when you actually have 2 square rooted n-1s, it's just 1 n-1, right? And so the n-1 in the denominator here cancels out with the n-1 in the numerator. So the formula, there's really 2 formulas here. There's the long formula where you compute the covariance and the two standard deviations. And then there's the short formula here where you actually just let the n minus ones cancel out. So you're still basically doing the same thing, but I usually like to use this instead of this. They're equivalent, but this one you just don't have to worry about n minus one divisions. Okay, so that's the formula for the correlation. Let's go see how we apply it. So the first thing we're going to do, notice I need xi minus x bar. And then I also need xi minus x bar squared. And I need to sum those up. So for x, I have an x minus x bar. I sum them up. So actually, I can just go on this page. And then I also have the sum of the squared deviations right here. For y, I've done the same thing. I have y minus y bar, and then I have y minus y bar squared. And then I sum up that information right here. And then the third thing I'm going to do, so the first two steps are univariate stats for x and y. The third thing I'm going to do is I've got to create this x minus x bar times y minus y bar column. So this is getting at the covariance. And then I sum that up and I get 52. So I know there's a lot of numbers here, but really if you're using Excel, let me stop share. I need to make sure I'm sharing my full screen. In Excel, this should only really take a minute, right? Like if you look here, I've got the mean of x is 4. So I'm just subtracting 4 from each. And then here, I'm just squaring it, right? So I'm pointing to D18, squaring it. And remember, you can drag these down, so you only have to really type the formula once. And then it's the same formula for y. The mean's different, 10.25. And then, again, so really, I know there's a lot of math, but I don't think it takes too long to do. So what we need to understand is I have confidence that you all can create these three tables. The tricky part might be plugging stuff in. So let's do this in two ways. The first way is the way I like to do it down here. So this is the same formula we saw above. So the numerator, it's the sum of the product of the deviations of x and y. Well, that number is 52 right there. That's this term, right? You can see I've taken the product of x bar minus y bar. So 2 times negative 0.25 is negative 0.5. This is positive 2.25, et cetera. And I sum them up. That's the sigma. I get 52. Now I need the square root of the sum of the squared deviations of x. So this part, where can I get the sum of the squared deviations of x? That's here. 84. Notice I'm just plugging in the 84. I'm just plugging it in. And then I've also got the sum of the square deviations of y, which is going to be the sum of the square deviations column. And then I just need to plug this into a calculator. And when I do, I get a positive correlation of 0.81. And you'll notice, again, it's positive. And that data above, you could definitely see that as x went up, y generally went up. Now, there's a longer form. You can also use the covariance form. And so in this one, you do have to account for the n minus ones. So here, let me clear my screen. So this part, we've already seen that this is 52. If I divide by n minus 1, well, there's 8 observations, so I'm really dividing by 7. I get this number, and that's my numerator right there. I can also do the standard deviation of y. So remember that the variance, how we go from 84 to 12, is we divide by n minus 1. So if you do 84 divided by 7, you're going to get 12. And then the square root of 12 gives me 3.8. 4, 6. You do the same thing on y, and you just plug in the two standard deviations. And again, you're going to get 0.81. So you can do either method that you like. I do prefer not accounting for the n-1. So what you're going to have to do, if you're using Excel, you're going to have to create these three tables, right? That should take about 3 minutes, 5 minutes. And then you have everything you need, and really just becomes plugging in and solving for the correlation coefficient. Okay, so that 0.81 is, we would interpret it as a strong positive correlation, and based on Cohen's 1988 guidelines, we would say it's a very large correlation between X and Y. Now, there's another way we can do this where we can actually z-score it, and this way is actually pretty easy. So remember, we've studied z-scores in the past. You center the data in the numerator, xi minus x bar, divided by the standard deviation in the denominator. So that is our z-score. This should not be new to us. So if I calculate z-scores of x and y, I take their products, sum them up, I get the 5.65 there. And then all I need to do there is divide by n-1. So I would do 5.65, divide it by 7, equals 0.81. So actually z-scoring is also pretty easy. Maybe, let me go over to this table. Maybe you find it a little quicker. And so again, how do I z-score? I take the x, I subtract the mean, which is 4.0, and then I divide by the standard deviation. And so I want you to notice that I'm using cell referencing. So I've locked in C61. So as I drag the formula down, you can see that only the first X, C55 here, that's the only thing changing. I'm always locked in, and you add a little $sign in front of, the mean and standard deviation here to lock them in. So you can also just type out -4 divided by 3.464. So again, it should be really just a minute to create these z's. Then you're just multiplying them, sum them up, divide by n-1, and that's a third method to compute the the correlation between x and y. And so the last thing I want to talk about when we look at this formula for correlation, what the correlation is it's actually the covariance between x and y divided by the standard deviation of x and the standard deviation of y. So we're actually standardizing the covariance. And this is why the correlation always goes between -1 and 1. It's a standardized measure. In the same way that the z-score is standardized because we divide by the standard deviation of x. Well, here we have to divide by two standard deviations because we're talking about two variables. And so, again, the covariance is kind of a confusing thing. It's really beyond what we need to know, but really the covariance is the same thing as the correlation. It's just not standardized. And that means the covariance can go on a scale from -1,500 to +32,000. It just depends on what y and x are. And because it has such strange scales, we don't really use the covariance much. But you'll see the covariance pop up in kind of more math problems. So now what we're going to do is there's a second Excel sheet I uploaded. It's got the same data. And in this one, we're going to be calculating the regression slope and the intercept. So we're going to use the same data, and we're going to compute the regression line, the line of best fit by hand. So remember, we have these formulas, and covariance of x and y and the variance of x. We have two sets of notation, which you'll see used interchangeably. So the little sigma xy or the sigma x squared. So it doesn't matter how you notate it. I'll probably do this in this course for the covariance. And so as we look at the formulas, we know we can't calculate alpha until we have our beta or our b. So we're going to start with the b. And here, what we need in the numerator is again, the product of, it's the sum of the product of the x and y deviations. So I multiply them and then I sum them. I get 52. So 52 then is going to be my numerator. I then need the sum of the square deviations of x. So I'm going to just add another column here, x minus x bar squared, sum them up 84, and I'm going to get 0.619 or 0.62. Oh, it looks like I have a typo here. 0.629. So I'll check that and fix that, but 0.62, right? That's really what we're dealing with here. And now I can get my alpha, so that's going to be really easy. Y bar, I have the mean as 10.25 and the mean of x is 4. So I'm really just plugging that in. So you can see y bar 10.25, x bar is going to be that 4. And then B I calculated in the step before as 0.62. When I put that together, I get 7.77. So what this means then, this is my equation for my regression line right here. Y hat equals the intercept of 7.77 minus 6.62 times x. So if I draw that, I would pause the video and see if you can draw this line without me. But what this means is that the y-intercept is 7.7. The line has a positive slope. Sorry, it has a negative slope. That is does that make sense? I see. I have a typo in the notes. This should be plus. So I will fix this. Plus 0.629 plus 0.629. And yeah, I will fix this in the notes. So the slope is 2-ish, right? And so that's going to be our estimate of beta. So for every 1 unit rise in x, y goes up by 0.62 units. And so again, this is our line of best fit, and it really should summarize the data. And if we go to Excel, let's see, I think one of these I added. So in the one with the regression slope, you'll actually see I've added in the line of best fit, and it actually like draws it on there for you. So again, you got the y-intercept, which Excel writes second, and then you have the slope 0.62. Now, the very last thing we need to calculate is r squared. We've already calculated the correlation. So it turns out that calculating r squared is just going to be taking the correlation and squaring it. So the correlation, remember, I think it was 0.81. 0.81. So if I go to calculator, 0.81 squared, oops, 0.81. Okay, it's not like 0.81. Let me tuck in squared. I get 0.66 more or less. 0.65, which again, so you're going to be noticing that the decimals are going to get slightly different things sometimes by like 0.01. We're not going to count off rounding, so don't worry about that. But you can see I just squared the correlation to get r squared. And how we interpret that is that this regression line describes or explains 65% of the total variation in y. That means 35% of the variance is unexplained. So the model I would say is pretty good. If you're explaining 65 with 35% unexplained, I would say that's pretty good. So I'm going to add in a note. So I do need to fix the negative signs here. And I'll also add in a note about r squared. I did not put the computation of r squared in these, but I'll add a little note. The last thing we do is we just demonstrate we had that formula that tells us how B, the regression slope, and R, the correlation, how they're related. And you can see in this example that you just plug in these numbers and you're getting the same thing. So what that means is, if you know correlation, you can get B with that formula. So we see a second formula for B below. It also means if you have the regression line, you can just get to the correlation really easily. So we want to remember that association going forward. So I'm going to add in a second practice problem, and I have a couple of corrections to make here. Everything will be corrected by the time I post it online. And that second practice problem, we're going to do in SPSS. Sorry, I'm going to do an SPSS example now. I'm going to let you do that, but I do suggest I would probably do this in correlation in Excel, but you could use SPSS. So the next thing I'm going to do is demonstrate this exact problem in SPSS because it is pretty easy. It'll just take a minute. Before I do that, I want to show you some cool software called Desmos. So Desmos here, I've plotted. So I've actually put in the data. So if we go back to this, I've got the X data 637, Y 10, 8, 14. I basically just put in the data there for all my X's and Y's. And then in Desmos, so Desmos is an online graphing calculator. You can see the URL there. You basically click on statistics linear regression and it kind of like sets it up for you to kind of learn. And I find Desmos interface really good and it's really good and easy to learn from. But you see here, they have the equation of a line, y equals mx plus b. But after I put in my data, they actually also give you the slope. So 7.77, sorry, that's the intercept. Using different notation, you're going to see that. So I've been trying to get us ready for that. So this is actually the intercept. You got to look at the equation to see that. 7.7, the same intercept we got earlier. And then the slope of 0.62, the same slope. That's what the line looks. And the residuals here are the difference between this point and the line, right? Those are our residuals. And the residuals have important assumptions about them. Next week, we're going to learn the assumptions. We'll be revisiting the residuals. You'll also notice it gives you the correlation. We computed it as 0.81, which is the same within rounding error. And then it gives you R squared. So Desmos is also a good tool to learn about this stuff. And the last thing we're going to do is we're going to learn how to do this in SPSS. And again, the class after this is regression heavy, and it focuses entirely on regression in SPSS. That's applied regression. I think it's 5122, HUDM 5122. So you're not expected to use SPSS, but as in the previous weeks, it's a very easy tool to use, and you can really check your work and just know you're getting it right. So I do suggest and recommend you spend a little time learning SPSS because as you're going to see, this is going to take a couple of minutes to do everything we just did in the last 15 or 20 minutes through Excel. So, as the 4122, we do have a very hands-on mathematical approach. We believe that by practicing the math, that it will make you a better understander, a student that understands this stuff a little bit better. So that's why we do the hand calculations. But once you leave this class, you're never going to calculate a t-test or regression slope or correlation by hand. You're going to use tools like SPSS. So I do think SPSS is worth the little minimum amount of time to be successful and use it in this course. I do think it's worth that. So this should open up any second. Always takes a while. Okay. SPSS open. I'm just going to hit new data set. Now what I'm going to do is I'm going to go to variable view. I'm going to create one variable named X, one variable named Y. The default numeric, that's good. And then the measure, I'm going to input as scales. So now you'll see I have two columns, X and Y. I think you could actually just start inputting data there, but what I need to now do is just take the data from the problem 6370, 6370, 6901, 6901, 10.814, 612, 13, 10, 9, and you'll notice it's got two decimals, and you can just make those 0. Okay, so there's my data. Now, if I want to fit a linear regression in SPSS, I go to Analyze, Regression, Linear. Then my dependent variable is Y. My independent variable is X. So the dependent variable, remember, it's the variable we're trying to describe or explain the variation of. And we're going to be describing and predicting values of Y with X. So if you think about the regression equation, Y equals alpha plus beta X, the Y depends on the right side. The Y is the dependent variable, the outcome variable. Y is the independent variable or the input variable. A lot of words we can use to describe X and Y here. I perhaps didn't emphasize that early enough. So I wanted to make sure I said that there. So Y is our DV, X is our IV. Now I can hit, I don't think I need to ask for anything, model fit. Yeah, we want that. Let me ask for descriptives. Continue, plots, don't need to make a plot. Now let me just hit OK. So you see, I literally just input the data, just put X in the IV and Y in the DV slot. You can see I get the same mean, the same standard deviations we saw in Excel. You can see I've got the same correlation point. So it's a correlation matrix. So Y has a perfect correlation with itself. X has a perfect correlation with itself. The X and Y correlation, which actually in there twice, we say correlation matrices are symmetrical. You see the correlation is about 0.81. Again, if you round it to 2 decimals. And then we come down here to the coefficients table. 7.77 is the constant or the intercept. A constant is just a number, right? So when we write the regression equation, the intercept is just a number in there, it just hangs out by itself. Whereas the beta 0.62 is the change in Y as X goes up by 1. So you can see here I have my X and my Y. And then these are actually this is the total sums of squares. This is the residual sums of squares, and this is the regression sums of squares. And so remember, we learned how to calculate R squared as the total sums of squares divided by the regression sums of squares. And if we plug that in, we get 49.5 over 32.19. And if I use a calculator, 32.19 divided by 49.5. Oops, typo. 32.19 divided by 49.5. I get 65%. So it actually just gives it to us there. So I have my correlation 0.81. And then I have my R squared, which is the squared correlation, 0.65. This means that the model explains 65% of the total variation in Y. So you can see SPSS, it's going to give you a lot of output. And again, like I've said in the past, you don't need to look at. But we can see that SPSS really just takes like a couple of minutes to really get these regression estimates out. So you are allowed to use SPSS and Excel. So on your homeworks, I would just ask that you include your work. If you do SPSS, show the SPSS output. If you do it in Excel, just put a few Excel tables in there and show us how you're using the formulas, etc. So at this point in the course, SPSS remains optional, but I will let you use it because this is going to really be the way you do it once you leave the class, which is now in a couple of weeks. So I will accept SPSS instead of handwritten math notes to calculate regression slopes and correlations. So before I leave, let me go ahead and show you. You can also just ask for the correlation. You notice the correlation came out here because I asked for it in the menu settings, but you can actually go to analyze, correlate, and then you can do bivariate, and then you can just arrow over X and Y, hit OK. And you get out this very ugly correlation matrix. This is a very big weakness of SPSS, but you can see X and Y correlation here at 0.81. And, I think either way to get the correlation is fine. I mean, I might just do this regression procedure because you just have to do it once. And then any question I could ask you, the data is basically here. Okay, so that's all for this week. Thank you all for attending and listening. And yep, let me know if you have any questions. I think this material is definitely a step up in difficulty, but it's extremely important, and really studying it and going slow on it will pay huge dividends as you continue to research as a grad student. All right, everyone, have a good rest of your week.